Okay. Today we are going to have a webinar around 1 hour. This presentation will be recorded, so you are going to have an available record then in our YouTube channel. So during the presentation, you can write down your comments or questions, and at the end of the presentation, we will answer all of the questions that you already have. And on the other hand, just give me some minutes to introduce our presentation in about 2 minutes. And if you have any question, just let us know through the chat. And please turn off your microphones. Yes, in order to have a better record of the presentation. So it's 3 minutes. In 2 minutes, we are going to start the presentation today. Okay, just let us know where are you from, from which country are you connecting to this webinar, and also in which department do you work in your company. You can write it in the chat. Okay.
It's important for me because in that way, to answer the question, I can forward answer in a better way because I will take in consideration your background. Okay. So many people we have here in the chat right now.
Okay. Okay. So in 1 minute we are going to start, and I'm going to start to record the presentation. So I just
from private funds consultant. That's very nice. A consultant, so they understand they ask for money and they want to buy an asset or something like that. Interesting. First time I have a person like Carlos Mercado that way.
Okay.
Hi, Alejandro. What is your background, just to know before starting?
Okay.
Okay. Well,
I think we are ready.
Ready to start. Yes.
Okay. Just let me start to record. Oh yeah, Jorge from Houston, currently independent consultant. His background is artificial lift.
Great.
Okay, so let me start to record the presentation. Okay. Good morning, everyone, and thank you for joining us today. And let me, to this webinar, what is the limiting factors for ESP design and operation with Master Science Sergio Caicedo. Let me introduce you quickly our company.
Myself first, and then right?
Okay.
Short video.
Okay, perfect. So let me introduce Mr. Caicedo. He's a physics and computer engineer from Simón Bolívar University at Venezuela, and he has a Master's Science in Petroleum Engineering from the University of Texas at Austin, USA, with 26 years of experience as a specialist in artificial lift and well productivity and software development applied to oil production. He has trained more than 700 engineers in the oil production area in the companies where he has worked. Mr. Caicedo has developed innovative projects working in multidisciplinary teams and has worked as a specialist in artificial lift in Venezuela, Kuwait, the United Arab Emirates, and the United States. And also he was awarded with the ESP Middle East Production and Operation Award in 2015 for his technical contributions and artificial lifting to produce hydrocarbons. So who we are UPC Global, a company leading in consulting that offers strategy solutions in artificial lift and production optimization. We supply hardware and software and provide training oriented to analyze and optimize the well's performance. Our mission is to satisfy our customers by providing integral solutions for the oil and industrial sector. We guarantee exclusive alliance with leading technologies companies while offering high-quality services supported by experienced team of specialists in each area. And our vision is to become a worldwide recognized leaders in the oil production business, always guaranteeing high health, safety, and environment standards for our employees and operations. We have more than 20 years in oil industry and have 4 bases in Latin America, Venezuela, Colombia, in Mexico, and also we have an operation in United States. With business in more than 40 countries, and we have some exclusive representations in Latin America, such as Ecometer. Our main services is field data acquisition, optimization, analysis, and elaboration of production plans, specialized trainings, presential and online version, also with our academy or in company online training, telemetry and automation, and also we have consultings and mentoring for petroleum engineers. And let me remind you that you can write down your questions during the presentation in the chat, and at the end of the session, we will answer all of them. Thank you for those who just joined. Thank you for being here, and thank you very much, Sergio, for your presence today.
Thank you, Marilyn, for the introduction. So let's go to the topic in detail. So today we're going to have a brief introduction. We are going to see the ESP components and their functions, classifying the limiting factors, understanding the limiting factors, prioritizing the limiting factors, considering limiting factors when designing, monitoring the limiting factors when operating, and final conclusion recommendations. So let's talk first a brief idea, because optimization is a word that many people use, but it's not properly understood and clearly defined. But so let's use the mathematical definition. When we talk about optimization, we usually mention to maximize or minimize a function which has many variables, and this function usually, if we don't have this, is free. The function has free, the maximum, we have to find the maximum in any place. But when we add constraints, we can have more than one constraint. We can have m constraint. Usually we are going to have, in general, less constraint than variables. If we have more constraint than variables, the system is static. We don't have freedom to define the variables. So usually the constraints are less than the functions. And in this way, that is optimization. So I have to have a function in mind to maximize, and constraints. That is math. And also, you remember that in calculus, that has to be with Lagrangian multipliers and so on. So if, for example, in this case, I have this function which has two variables, x and y. This is the graph of that function, okay? And then when we consider that the function is restricted to some value, then it's different. The initial function, if I consider the function has no maximum, because it goes to infinite when x equal to infinite and y equal to 0. But if I introduce some constraints, then the problem changed a lot. It's no longer infinite. The maximum D function is going to be, where is it going to be? Well, sometimes we can compute some derivatives, but sometimes we can do some observations. For example, if we notice that x is always positive, so x squared will always add. It doesn't matter if it is -5 or +5, whatever value we have is going always to add. So for maximization, I want to increase that to the maximum absolute value, as least as possible. On the other hand, minus squared is going to be always negative, always will subtract. So for maximization, I want to be the closest value to 0, because if I have -5 or +5, it's going to be -25. It doesn't matter. So for maximization, if you pay attention to the function, I want to have this value to 0 and this value to go to the top. And then we're going to see here x is this axis over here. This is y over this direction, and the value I'm plotting in C, the function in C, just to see. So this value is going to be -5 and +5 when y equals 0, you are going to have the maximum value of that function that is here. Okay? So this is the graph, and then you are going to see here the same table. I'm going to see that the maximum is this. When you pay attention here, for a given value of x, always you have consider a column for a x fixed. The maximum is going to be when y equals 0, as I told you. Okay, and so the maximum has to be over this, and then you're going to see that the maximum is 25 and 25. These are the two maximums of this when you have this function subject to this. What if the function, the condition changes? So, for example, if I have x between -5 and 2, and y between 2 and +5, so I want to minimize y, so it will be in y equal 2 and x equal 0. You want to see and x equal to -5. So y equal to, you're going to see this is the value. 21 is the max between 2 and +5. So y has to be, the minimum value is 2, and x is going to be -5. So we're going to have 21 as the maximum value in this cell. So why I'm telling you, because when you have you're an artificial lift engineer, then keep that in mind. When you optimize, then you have to keep in mind what is your function. What do you want to maximize? Then in general, if you don't have clear that, by intuition, we are going to do maximize the favorable and minimize the unfavorable, as I did in this example. Okay? So, but in reality, we want to maximize production because that is our extend run life. But in reality, when you consider this, I am maximizing the net present value of my asset. Because if I'm producing too much and the run life is too short, then I have too many work hours, and then the economics is reduced. So I have to reduce the lifting costs, resources, power, gas, in the case of gas, logistics, manpower, reduce the deferred production on off time, minimize operational issues. But then I have to keep in mind what are my constraints, subject to limiting factors, power, capacities, quota, stresses, etc. So remember, anytime you are optimizing, you have to keep in mind what your limiting factor, because that changes the maximum value. Okay, it's the same. So we have to understand, as we did here, we understand what are my constraints. I need to understand what are my constraints. we must understand the limiting factor to achieve the ESP optimization. We must understand each ESP component, its parts, and the way it works. We must understand ESP working principles and phenomena. We must understand how ESP and reservoir interact with each other. We must understand the effect of exceeding each limiting factor. We must understand how component part could fail and why. We must list the list of total possible failures and how likely they are to fail. There are no specific factors that we have to keep an eye when dealing with ESP, because surprisingly, there are several limiting factors to consider when you design and operating ESP. Many of them are interrelated in not a simple way. Clearly, when a factor is not considered or misinterpreted, then the consequence could be a ESP system facing problems, unable to reach the target rate, and or having a shorter life than expected. For this reason, engineers must understand ESP working principles, phenomena, equipment components, their function, as well as having an integrated view with the reservoir. So let's understand the components and the functions. So downhole, we have the power cable. This transport energy from surface to the downhole motor. Then we have the centrifugal pump, the multi-stage centrifugal pump. The objective of this is provide the head of pressure gain between the intake to the discharge, that is the, okay? Then we have the gas separators, or sometimes we have only the intake, but when we have an intake, we have natural separation, okay? So expel most of the free gas to the annulus to avoid this gas coming into the pump. That is the objective. Transmit torque to the pump shaft because the separator is in between, so also to transmit power to the pump. The steel section is in between the intake or gas separator and the motor. First, allows oil thermal expansion, support the pump shaft acts as a load. When you are pumping, the shaft is going to exert force down. So in some place you have to support that force. We call the shaft as a load. Makes pressure inside the motor equal to the pressure outside the motor to avoid reduces mechanical stresses in the motor. Avoid motor oil contamination, and also to transmit torque to the separator, to the pump, or okay. The shaft is passing through all of this. Then the whole motor provides mechanical power, torque to rotate the shaft, to move the seal, the separator, and the pump. And then the downhole gauges that provides downhole operating values. These are the parts in the surface. And we have something that is on the downhole, and this is at the surface. We have the primary step-down transformer. Usually that is provided by the energy company, or if you have your own generator, then maybe you don't have this, okay? Then we have the objective of this is to reduce from maybe 13,000 volts to 480 volts. Then you have your VSD. The objective is to change frequency and provide power for the ESP motor. Then we have the secondary transformer. The function is to increase from 480 volts from the VSD output to the motor voltage that depending on the motor could be something between 900 volts to 4,000 volts depending on the motor. Then we have the venting box that is just to avoid gut leaks through the cable to reach the power skid, all of this to avoid the explosion. Then we have the sulfur cable penetrator that is just connection from the surface cable to the downhole cable and providing integrity to the well. Let's classify the limiting factors. The limiting factor to keep in mind when you are designing and operating can be listed and classified in the following categories. Related with the pump selection, related to mechanical strength, related to operating condition, related to energy requirement, related electrical roll life, and completion. Let's go to those related to the pump. The components are the pump components are the impellers that is rotating. That part that's here, we call the diffuser, the static part. We have the washers, this brown, the housing of the, or casing of the pump, the housing. We have the shaft that is here, the compression, and the bushings, okay? That are not showing there. So we have to know that there are three types of impellers: radial, mixed, or axial. The type of impellers for the GDF, but also you have to take care with the GDS and the sun capability, the design of these impellers. Okay, some they are better for sun and the materials. The floating or compression assembly. The pump can be assembly floating. In this case, the impeller can move a little bit free, but in the axial direction. When you are in compression, it's attached not only radial, rotating, but also axially. Okay, that is going to change the load in the shaft. It is floating, the load in the shaft is less. If they are assembly, compressed assembly, they are going to add more load to the shaft. We have to understand if our pump is uniform, same diffuser type model, or we are going to change one model at the bottom and one model at the top. That is one case, for example, where the gas handler reality is a taper pump at the end of the day. Maximum pump section length. With the pump, the housing, we have different lengths. So the maximum length of the housing, let's say, is 30 feet. So that is going to limit the quantity of stages you can introduce inside that housing. For the same series OD housings, there are different models of pump, and depending on the model, this height of the stage can change. So the number of stages that fit into a housing depends on the model. Okay, so you are limiting the number of stages due to the housing. The maximum workover length. Sometimes that is a problem when you are assembling the pump. So if the rig is not too tall, then you cannot have a very long housing. Maximum pump diameter and shaft that fit in the casing, considering the installation and well trajectory. This is very important. Sometimes they're telling you that the casing is 7 inches and you have a plenty of space, but in reality, you have dogleg severities, and then at the depth that you want to install the setting depth, then you cannot have for example, a 5.38 pump because of the dogleg severity, because you want to go deep and you have to run the 4 inches pump. So that's important. The pump diameters and rates are related. For a given diameter, for example, pump of 3 inches, and depending on the frequency, but at 60 hertz, probably you cannot handle more than 1,000 barrel, 800 probably. And if your speed is lower frequency, 40, much less. Okay, but also depending on your motor, because nowadays there are motors that assist to a conference, and there is a new pump that they can run at 5 times, so they can run at almost 300 hertz, which is 1600 RPMs. But it's a very new pump. But the new pumps with permanent magnetic motors, they can run easily 70, 80 hertz, okay? The materials of the oil reels, there are some oil reels in the housing, the material of the washers, the material of the pump, the material of the shaft. We have a standard shaft that supports some torque, and we have a special material that can handle more torque. Then keep in mind the affinity laws, that the power that the pump requires to pump goes to the frequency, to the qubit of the frequency. So if the power at 60 hertz in one pump, one stage is 1 HP, 120 hertz, just double, it's going to be not the double, it's going to be 2 times 2 times 2, so it's going to be 8 times the power. So this is cubic. The pump head, or the pressure gain, grows to the quadratic of the frequency. Okay, so what I'm telling you here is usually the catalogs, they give you the values at 60 hertz. That's why I'm typing here 60. The pump rate is the rate at 60 hertz. Then you have to correct to this is not cubic, sorry. This, I don't know why is 1. Oh my God, sorry about this. Typo error. It goes linear to the frequency. So, and there's a range for the pump. The pump can have a long value. The rate can be any value, but the recommended value is something else that we're going to see. But depending on the frequency, those limits are going to change. This is what I'm telling you. This is for example, for this pump, the recommended value at 60 hertz is this is 1,100 to 1,300. Let's see. No, this is 1,050 to 1,350. Okay, this is the recommended range. The pump could be working here by accident or by few seconds. By the way, when you start a pump, initially it's here. In that rate, the initial rate is going to be instantaneously here and then moving to the operating case. Okay, but the recommended range is not the same that the operating the reality. Okay, and this is a total rate at the bottom hole. It's not downhole rate, not surface rate, and considering water, oil, and gas passing through the pump. So you have to keep that in mind. You should work in here. If you're not here, you're going to reduce the run life. Okay, that is the problem of the. Let's go to the seal or protector. The protector here, this is the cross bearing here. So the axial load of the pump in the shaft is going to be supported by this cross bearing that is in the end of the protector. Okay, so this is a limit, and this load, depending if you are having a compression or floating assembly, the number of stages that you can support in floating is higher than the number of stages that you can support when you have compression. And when you use compression, when you're handling solids, you are going to use compression assembly to avoid the friction between when you are having solid, you are going to have a compression assembly to avoid contact between the diffuser and the impeller. Okay, so but the price of this is that you cannot add as many stages as you have in floating assembly. Then you have to take, you have bags inside. What is the maximum temperature of the bags? If you have labyrinth, what is the maximum inclination that you can have a labyrinth inside. You have mechanical seals and bellows. Then you have to think about the maximum new temperature that you can handle. This is used for SAC-D, the bellows, in SAC-D in Canada, so they can support a very high temperature. And then you forget about the bags in that case. Then you need to know the volume and density of the electric oil here, depending on the size of the seal section. Then the number of strips you can have before having oil contamination in the complete chamber is higher than if you have a small volume. If you exceed any of the cross-bearing load, then you are going to reduce the run life. Let's think about the mechanical stresses. Then there is one that is maximum quantity of solid. That is, you have to measure that in parts per million. Usually people does not measure that, but you should do it. At least have an estimation. There are some online measurement devices that the surface. They are qualitative, but they are not quantitative. Okay, but you have an idea what is happening in your well, at least. Then the maximum differential pressure. In blue is the intake pressure. That is, you can see that is the pressure you see at the pump intake. And in red is the pressure at the pump discharge. You have, for example, a 500 psi intake. At the discharge, you have 7,000. Maybe this differential pressure is too high for the pump, and then you have a problem with you're going to have a problem. You're going to see the burst pressure, and then the housing is going to fail. Okay. Then you have the maximum axial load on shaft. What I mentioned to you in the previous slide, the shaft is having I put it here, down force always. The shaft always have a down force, okay? And this is going to be supported by the thrust bearing. Then the maximum torque that you can handle in the shaft. That shaft is normal shaft or high strength shaft. In the catalog, you can see how much they can support. And then something I want to explain you, because this is not really clear. In reality, the shaft can handle torque in reality. What happened is that this torque, using this equation, can be transformed to power. So notice that the maximum power of the shaft depends on the friction, but the maximum torque does not depend. It depends on the frequency. Sorry, friction, the frequency. The torque shaft here does not depend on that. That is a property of the steel, the material, the diameter of the shaft. That depends only on that. This is a constant, the maximum torque, and then depending on your frequency, you are going to see. When you see the catalogs, you're going to see that in the pump, they're going to show you maximum torque 50 hertz, 100 HP. Maximum torque 50, and usually they show 50 and 60. 60 hertz, 120 HP. So how is it possible that it gives you an idea that the shaft is become stronger? No, shaft support the same shaft, the same torque, but you are changing the frequency, so it's an apparent way that you have more capacity, but in reality, not. Okay? If you exceed the torque, or normally you exceed the power at that frequency, then the shaft will break immediately. Not in the run life is going to be, as soon as you exceed that, you are going to damage the shaft. That's why you have to take care when you start in a pump. It's very important. So that's why you start a very low frequency, and then to have little stresses, little differential pressure, and so on, little power required, and then you increase the frequency in a ramp, because the peak in torque could be very big, and you're going to break, even if your static torque is low. The dynamic torque it could be very high, and then you can break the shaft. The rotary gas separator. Each series of diameters, they have a maximum flow rate that the separator is going to work properly. If you when you are in the range in the flow rate, then the separator is going to have a very high efficiency, about 90%. If you exceed that, if you are above, not below, above, then the separator is not going to work, and then you're going to have only natural separation, which is 30%. That could be the immediate problem. Maybe you can exceed the maximum gas volume fraction, the GBS, and then you can have problems. You can have a gas lock in the pump because you exceed the capacity of the separator. Rated operating condition. The GBF, oh my God, the gas volume fraction, you have to keep an eye in that. At the intake conditions, when you change the intake pressure because you increase the rate for the same UR, you want to change that, okay? The recommended production rate is going to change the intake condition because the inflow performance is associated with that. If you not are in the range, then you want to reduce the run life. If you exceed the GBS, you can have a gas lock condition, and then you can have a problems with your pump. You're going to have to trip the pump. If you have a gas lock condition, you have to trip. Then starting line, if you don't trip, then you are going to overheat the motor, and then you can have a failure in matter of hours. Okay. Minimum intake pressure. The minimum intake pressure is associated with gas. The lower the intake pressure, the higher the free gas of the pump, and it's also related with submergence. Let me explain you this. You can have a water well with no gas, but if I don't have liquid at the pump, then I got what we call pump off condition. And this value has to be analyzed with the casing head pressure. I'm going to explain that later. Having only intake pressure is not an indicator that you are right. Okay, you can have 2000 psi intake pressure, and maybe you can have no liquid at the pump. I'm going to explain that later. Viscous oil. The viscosity reduces the capacity, the recommended range capacity in rate, and reduces the rate and increases the power requirements. The water cut change the free gas, also increase the power consumption, okay, but does not change the pump head. Okay. CO2 and H2S production, just the run life is affected by corrosion. The required head, if I cannot provide, this is the dynamic level. If I cannot provide, the pump is not able to provide that dynamic level you are not going to reach your target rate. Certify the inflow performance with suitable target rate. You can have a pump of 4,000 barrels, 5,000, 10,000 barrels, but if your your reservoir can only give you 500 barrels at zero downhole pressure, there is no pump that produce more than that value because that is the reservoir limit. So you have to be sure that your pump is suitable with your target rate and the inflow. They are properly, they match each other. Satisfy the inflow performance with the target rate, which I mentioned. Velocity of the fluid to cool down the motor. If the velocity is too low, maybe it can overheat the motor. If you don't take actions, and we have motor overheating, then you have the following problem. You have to, if you don't stop the pump or do something, then you have a failure, a matter of hours. Then the other option is trip the motor. You have the protection. Then you have downtime and run life. You have many trips, the run life is going to be shorter because too many stretches in the shaft. The motor oil is going to be contaminated faster due to the thermal expansion and cooling in the protector seal section. Okay, the motor limiting factors related with energy, power, surface related. The first one is the power at surface facility has to be higher than the power that your motor requires. And the power that the motor requires has to be higher than the power that the pump requires. Notice that the power surface does not change with frequency. The motor power changes linearly with frequency, which is the last equation here. The pump consumption, remember that changes cubically with the frequency. So we have a problem here. The one that grows faster is the pump consumption with frequency. Then the motor and the surface power capacity does not change with the frequency. So we're going to have a slide with this. They have to take care with the maximum winding temperature that depends on the manufacturer, tell you how much your motor is able to handle temperatures. The problem is the isolation inside the motor. Then if the isolator has a failure, then you have a shortcut and the failure is immediate. Fluid cooling velocity, you have to be sure that you have cooling enough. Motor voltage, what's the minimum, the maximum nameplate, and then you have to take care when you have the rating. The rating applies when your motor H power is very high for your application for some reason, design problem or something that happens, then your currents are going to be very low. So you have the chance to reduce the voltage at the surface and the rate the motor. For example, a 4,000 motor with the nameplate 4,000 volts and 100 amps, but your application is having 10 amps, then you can reduce the voltage to, let's say, 2,000, and maybe the new current is going to be higher, but the power at the end of the day, the power is going to be less. Okay, that's the nameplate. We do that on purpose when the motor is oversized for the pump or the well. Okay, motor current, what is the minimum, the maximum, and the nameplate. Motor heating, remember that motor heating is the energy that your motor is generating as a heat. Essentially, it's your power of the motor 1 minus the efficiency. So if my motor is 80% efficient and I have a 100 HP motor, then you have a heater of 20 HP downhole. Okay? If I have a higher efficient motor, I change for another that is 95 5%, then for a 100 HP motor, I have a heat of 5 HP heater, which is 1/3 of the other. So the general, the heating power is going to be less for the same HP. And the motor power in the shaft, as I mentioned, change linearly with the frequency. When exceeding the overheating, then you have trips. If you don't trip, the trip fails or the alarm, the setting is not properly done, then you have a shortcut. Or if you don't reach that critical condition, then at least the run life is going to be shorter just because of the trips and because of the degradation of the materials. We're related with electric specification. Then we have surface operating voltage after step-up transformer, not the VST voltage, after the step-up transformer. We have the motor nameplate and operating voltage. They are different, okay? The cable nameplate and the operating voltage. The voltage in the motor is equal to the voltage in the surface minus the voltage losses in the cable. So we have to be sure that the voltage motor provided by the surface is operating should be close to the nameplate voltage of the motor, okay? It is too low, then you have problems. Maybe you cannot even start you cannot start the pump. Motor operating voltage equal to the nameplate or less when the rating, but check the current as I explained before. The rating, as I told you, but you have to check the current load if the operational current load before the rating is too low, then you can do the rate. You have to check that the cable operating voltage is less than the nameplate cable voltage. If you exceed that, then the isolation of the cable is going to fail, and then you're going to have a shortcut. The operating currents must be less than the nameplate. There are no problem to be very low of the current. If your cable can support 120 amps and you are having 10 amps, there is no problem with that. Just by the way, for the run life, it's better that cable is not going to fail. That cable is very difficult, but it's a matter of capital expenses. You pay for a very expensive cable that you don't need. But by the way, in Abu Dhabi, we used to have always cable number 1, even we can have cable number 4, and then we never have failures in the cable, never. So you can pay a little bit more for the complete capital investment. Is little compared with the workover and everything. So we go for that. The motor nameplate, operating nameplate current, all the current has to be lower than the nameplate. For the cable, for the surface equipment, for everything. Okay. Related with run life and reliability. Maximum motor operating temperature, maximum mechanical vibrations, electric integrity motor cable, check your arms, check how is the health of your cable, and sound handling capabilities. Then check the materials, check the assembly use. You have some use compression type pump assemblies. Related with completion, maximum dog leg severity. For that one, those the people they say like 10 degrees for every 100 feet. But that is a thumb, just an approximation. But in reality, to know what is the maximum, you need to know what is the pump length, what is your pump OD, what is the casing ID, and then compute what is the maximum duct flexibility you can have for your pump, considering your OD, ID, and the pump length. If you don't ignore this, then you are going to bend the shaft during installation, and probably maybe the cable can be damaged too. But at least the shaft you are going to bend, and the vibration and the run life is going to be shorter. The casing ID tell you how big is the pump you can install, and the pump diameter is going to tell you also the maximum rate for that diameter that you can handle. If you are going to use white tool, is required or not, then it's going to change the pump size and the motor sizes. The maximum setting depth, which is related with the duct severity and everything, it's going to change the restrictor rate and affect the gas volume fraction into the pump. The packerless or downhole packer, if you're going to use packer downhole or not, is going to affect the GBF, because you cannot, if you are to install a downhole packer, you cannot install a separator, so all the gas, the free gas, have to be handled by the pump, which includes the GBF. Okay, it's going to be run or flat cable. Capillarity or control injection lines, you need to know that if you use flat cable, then you want to deal with electrical balance. If you have round cable, you have less problem with this, and of course a space problem. Prioritizing limiting factor. What is the most important limiting factor? Well, as you can see in the apply the proverb, a chain is as strong as its weakest link to ESP design. Okay. The ESP is constrained by the most limiting factor. So we need to know what are the limiting factors in the ESP and keep an eye on those that are reaching critical values. Okay, I'm going to give you a very important example here. For example, in this case, I compute the maximum stages that you can handle with an example of design. The protector can handle 749, the shaft 268. The motor can give you 490. The pump length, you can have a stack 470, and the housing 325. So the minimum of this is the shaft. So I can only have 260 stages. Otherwise, you're going to break the shaft. It doesn't matter if you have the protector is okay and the pump is okay. You're going to break the shaft. So keep an eye in that one. If you want to improve that, then you have to say, I cannot use this shaft. Use a higher strength. How much is the higher strength? Maybe 300. So in 300, still having the shaft is going to be, if the highest strength can handle 500, then the next lower value is the housing pressure, the differential pressure. So you have to do something with your housing. You have to do something, or you have to live with this. Okay? So this explains exactly this slide and this photo. Let's consider, when you are designing, let's consider the HP loading. And then at what frequency are you designing? You want to see two slides, very important. So in this, you're going to see the pump consumption power as a function of frequency for a given number of stages. Let's say we have 200 stages, and that is the power. Okay. So as the frequency, the pump consumption depends on the frequency to the cube. That's why you see the black line growing very fast. The non-motor power grows linearly with frequency. Okay, at zero frequency, zero power. Okay, and the VSD is constant independently of the frequency. Okay, so in this case, if this is my power in the BSD, the maximum I cannot work at this frequency, the intersection point between the blue and the black, because at that point the surface can give me the power for the pump, but the pump is consuming more power than the motor can deliver. So this intersection point cannot be handled. I can handle at this. Let's see what happens if my BSD power is on. So the maximum frequency I can work here will be exactly the intersection of the 3 points. If I reduce the frequency, then the pump consumes less power than the power that you can provide by the motor, and much less than the power you can provide by the surface skid. What if the BSD available power is this? So in this case, the intersection, if I use the intersection of blue with the black, at this frequency, the pump is handling using this power at that frequency. The motor requires is going to provide this, so the power is going to be as this. So I cannot work here because the motor requires more power than this one. So no, the motor has capacity to provide more, but the BSD cannot. So here in this intersection, the BSD can give the same power that the motor can supply, and the pump consumes less power. So it's something in between, but I'm sure this point, if we are here, because in this point, this is the capacity of the motor to deliver, but this is at some point in between, probably is the one point that the BSD can provide the power that the motor is able to provide, but the motor, since the pump is requiring less, so the motor is going to be able to work. But by sure, between these two, not this, probably very close to, you want to be sure the maximum frequency is going to be here. Okay, so that's important to know the affinity laws. Okay, so just as to show you, suppose what is the frequency you are going to design. For example, if the load factor at 60 Hertz is 100, then it's impossible to increase frequency, because when you have 65, the pump is going to require this in your motor, so you cannot. Okay, so if at 60 Hertz, the only thing you can is reduce frequency. As you can see, when you reduce frequency, at 60 Hertz, then the motor is going to have more power than the pump, as you can see in the graph. If the load is 75% at 60, then you can increase the frequency up to 70 Hertz, a little bit less, 69 probably. But you cannot 75, no, over 69, 70 maximum, okay? If my lower power load factor at 60 Hertz is 50, that means that you have power in the motor to increase up to 80 Hertz, as you can see. So take care with the load factors and the frequency you are designing, okay? When you are designing, then pump selection for your ID, what frequency are you designing to reach the target rate, which is the design frequency? Some people in Middle East, they design at 50 Hertz. a design frequency. Here, US 60. But be sure, check, depending on your application, maybe it could be 70, maybe it could be 40, I don't know. But check what is the frequency you are designing as a reference point, starting point. The pump must provide the required head pressure gain, differential pressure between the discharge and intake to produce the target rate. And this differential pressure has to agree with the no analysis. What is the expected pressure in the tubing for that target? What is the pump discharge? What is the expected pressure for no analysis at the for intake pressure for that target rate? These two things must agree, they must match. Check for the maximum GBS, free gas into the pump, that the ESP can handle. Not the GOR. Do not check for GOR, please. You can send you as a reference to look for the webinar, EIPR GPC webinar. It's on in the web page on the YouTube. Check for that webinar. I can show you cases with very high GOR and you don't have gas at all in the pump. If your GOR is very high, but you are above the intake is above the boil point, you have no gas. And all the way around, you can have a low GOR 200, but your intake pressure is 100 psi, and you have a lot of gas. Okay. So check GBF, not GOR. The setting depth, the target weight, the IPR curve, and the GBS are interrelated. They are not separated values, and all of them must have a physical value for the ESP. Again, check for that webinar we gave in the past. Check for correction factor for high viscosity, heavy oils or emulsions with light oils. You can have high viscosity with light oils if you have emulsions, okay? So that changes a lot the capacity, the correction factors in head, in rate, and power. Try the bigger pump OD to have the bigger shaft if you can. When having uncertainty in the reservoir pressure and productivity index, select the lowest value of both because that will be the most severe condition for pump head, free gas, and power requirements to avoid unexpected limiting factors. Sometimes people is too overconfident and they use very high reservoir pressure, a very high productivity index. And then in reality, when they go to, they are less. And what happens is that for those values, you are going to reach the power limit or the head limit or the burst limit. You are going to get surprises in the limiting factors when you over predict the reservoir pressure and productivity index. Take care with that. Select the load of the motor at the design rate and frequency to provide flexibility to increase the production rate in case productivity index and reservoir pressure are higher than assumed. What I mentioned here, okay? Try to use the highest voltage, lowest current motor for the required HP, but check for voltage limitation at surface while considering the cable voltage drop. Okay? Sometimes there are HEC restrictions in especially when you are in platforms and there is a lack of space. Usually they avoid having high voltage because people who pass next to that place is matter of HEC safety rather than engineering. Okay? Sometimes you don't have the step torque transformer that reach very high voltage. You don't know. You have to check that. How the design limiting factors order from the most critical to the most relaxed, so you know where to keep. Okay? The limiting factor during design could be different from limiting factor during operation as production conditions change with time or due to the uncertainty errors in design data. Update your well model with recent and accurate data. And update the list of limiting factors and identify the critical and relaxed factors. Update your alarms and treat values accordingly. Some variables take months, years to change, the reservoir pressure, for example, while others could take hours, the downhole flowing pressure or the casing wellhead pressure. Take care with that. The more data you monitor, the better. The more you have online, the better. However, some of them will be manually and monthly valued. Production tests, for example. For those, try to get estimate from your online values if possible. Here, where to keep an eye. This one is a real case, okay? We simulate with design. This is for design. You have here the whole pressure, rate, gas, frequency here, the intake pressure, submergence, that is the liquid above the pump, dynamic level, and total rate, free gas at the pump discharge pressure, dynamic head. So let's see what happened. Here you can see that for intake pressure you cannot exceed 66 hertz, otherwise you're going to have a problem. For the submergence, you cannot exceed 60 hertz also. By the way, you have 71, then you have no fluid at the pump at this value. Okay. Here, what happens here is when the frequency is too low, you are working in the very low range and you are out of range below the range. And here you have how far you are below the range. You are 33% less than the minimum value at that frequency, okay? Here you are going to see that the frequency, the minimum and maximum rate change with the frequency, okay? So this alarm is not simple to use a single value because the frequency changed the limits. Okay, I did on purpose to show you that. Here you want to have the rate, total rate divided by the maximum rate. This is total rate divided by the minimum. When you are below the minimum, you are a problem. When you are below the maximum, it's not a problem. So this pump will never have a problem exceeding the maximum rate, but will have a problem handling minimum rate. Okay. The discharge pressure here I have is the maximum differential pressure that with that pump I can handle considering the number of stages and the head. And here's the dynamic head computed from the inflow and outflow. And here you want to see what happened with the head. A low frequency, the head is low because it grows as a square. So maybe a little 90%, 85% of the maximum. Here is the power that the pump is going to consume. Here is the power in the shafts at 60 hertz. And here I'm going to see the power in the shaft at the frequency is in some place. Here is percentage. So the shaft is not going to fail ever, never, even a very high frequency. The shaft is not a problem for this design. Let's see with the amps. The amps start having an alarm here, depending. I put an alarm at 90. So you cannot exceed 16. 3 amperes going to start being a problem. Here you can see the current. Okay, the current nameplate does not change with the frequency. Very important. Okay. Let's see the HP in the motor. Here you are going to have a yellow, it's not a yellow because the motor is not going to fail, but you are under the motor is 29% load. So the efficiency of the motor is very low. You are you can derate if you plan to or at this frequency, you can derate the motor, okay? But this motor will have a problem more or less in 65 hertz, okay? The temperature of the motor, interesting, at low frequency, the temperature is higher than high frequency because of the cooling. So here in my list, I will have the free gas is depending on your pump. If you use pump that can only handle 10%, which is radial impeller, then you cannot exceed 57%, 57 hertz. If you can handle 20, then you cannot exceed 65. In this case, it was a mixed flow type. So we can, for all the meter, we can see that 60, but I will keep an eye in the motor, amps and load here. Okay. What if, by the way, what is the casing pressure for this pump? The casing pressure for this wellhead casing pressure is 220. Why? Because when you have 220, the fluid level is 0. Okay, so the wellhead casing head pressure for this example is 220. What happened if the casing head pressure is 1,300 psi? That means that when you have 100, 300 here at this rate, you have no liquid in the pump. So if you have this pressure in the casing, my limiting factor will be the submergence, and I cannot exceed more than 49 hertz. This is very important to understand. Okay? Conclusion and recommendation to finish. Understand the ESP working principle, component, and associated phenomena is crucial to understand the limiting factors and their effects. Knowing the limiting factors in design help to understand the forecast, the risk when selecting equipment and materials. Having data lists of limiting factors in each well is highly recommended during operation to know the weakest component for proper monitoring to keep an eye in those critical. There are values that must be analyzed together, such as casing head pressure and pump intake pressure, because only pump intake pressure cannot detect a normal situation, such as venting valves closed. Understanding limiting factor helps to understand and develop smart alarm algorithms rather than having a dashboard with alarm with constant set values. Well, that's all for today. Do you have any questions? I'm happy to answer.
Thank you very much, Sergio, for your presentation and deep explanation. So yes, there are some questions here. Just give me a moment, please. The first one is from Leonardo Sevillano. So he's from Venezuela. He said about motor coiling velocity. Most of manual talk about 1 feet per second of.
Okay, if you attend to my course, I will explain you that. But that is a Thuma rule. Okay, what happened? First of all, what in reality happened is that you have to check for your temperature. By the way, there was I can suggest you a paper that was presented by Suchasin of ConocoPhillips. In SACD, they have a very fantastic case. But it's a very specific case for SACD. Okay, they keep the well shutting for 3 months. So rate equals 0, velocity equals 0. And the pump and the motor didn't fail. Why? Because that rules has too many things. That's why you have to understand the limits. First, what is the temperature of your environment? The temperature of the rock at the pump setting depth, not the temperature of the reservoir. Because maybe the reservoir is at 10,000 feet and your pump is at 7,000. What is the temperature at 7,000 feet? What is the temperature, maximum temperature that motor can support. What is the efficiency of the motor? Suppose that you bring a motor from an alien planet and you have 100 efficient motor. So the motor will never generate heat. So you can have zero velocity. Okay? So if you have a permanent magnet motors, they are 10% more efficient than the induction motors. So second, what is your water cut? The limit for oil is not the same that limit of water. Water is very good for cooling. Oil is not good for cooling. So the limits are different. So in reality, the rule, I can show you that in my course. What I tell you is that after 1 feet per second, you don't get more cooling. I mean, it's the same to have 3 feet per second than 1 feet per second for cooling purposes. Below 1 feet per second, you have less cooling, but you need to know what is the internal temperature. The internal temperature depends on the external temperature of the rock at that setting depth, not the reciprocal. Depends on the velocity or the heat transfer coefficient of that depends on the velocity, depends on the motor HP power, depends on the motor efficiency. And finally, that final temperature you have to compare with your temperature of your motor. There are motors that they can, for example, for SAC-D applications, they can handle 500 Fahrenheit. Suppose that you install those special motor for SAC-D application steam operations, and you are in your well at your setting depth, you have 200 degrees. I bet you that even you have rate 0, and you keep your motor, if you are producing, probably the temperature of the motor is going to be maybe 220. Okay, with rate 0, maybe it's going to reach 400, but after 400, it's not going to increase more the temperature. But that special motor can handle 500, so that rule is meaningless. But if you install a motor that burns at 330, yes, of course you cannot have that condition. So that is just a reference. You can have less depending on your motor. There's another case in Kuwait. They have for 3 years, the motor will, I guess, 0.25 feet per second, and it's working because it's a permanent magnet motor. It generates less heat, the temperature of the environment is less, and so on. That's the answer.
Okay, Sergio, thank you. We have 2 more questions, so let me write to you the second one from Leonardo also. He said about motor coiling, what is your opinion about the rate ESP motor? How much a motor can it be derated? I can write for you this.
Yes, I understand. Yeah? Okay.
Okay.
Again, you have to know a little bit electricity. Okay. Remember that rate, that voltage times current is power. Okay. So what you have to be sure is that you are not going to see never the maximum rate, the maximum current of your motor. Pay attention here. Let me go back. This one. You pay attention here that the current, maximum current, does not depend on the frequency. Why is that? Because the current is related with the size of the Cooper, the conductor size in the winding. So suppose that your windings, they have a cable this caliber, okay, which is very small. So in this cable, you cannot exceed, for this thing, more than 5 amperes. Okay, if I use a cable this thing, then you can handle 50 amperes. Doesn't depend on the frequency. Okay, so if your motor right now, in this case that I'm showing here, for example, you are going to work at 43 hertz. Okay, so the motor is 29% of the power at that frequency. So you can reduce the voltage in that motor to the half of that, and the current is going to be the current. This motor can handle the current here. Current 64. No, this one maybe you can increase the current 30%. So you can decrease the voltage in 30% of the voltage of this motor, and the current is going to increase and is still in range of the current. So you have to do the math with the current, because what you cannot exceed is the current. Okay?
Okay, Sergio. Thank you. And the last one, let me write here for you. I think it's much better if you can read this question from Laura. She's from Colombia.
Laura Cristina Garcia. We have already channel application in pretty well. No, we still want to this question. The question he's doing is I cannot do the math here. I have to do the design, because without that I would just having comments without any support. I believe the system is not the best choice, probably, but I have to prove it. Okay, and that is through simulations, designing each method. Okay, and then you compare. My opinion is design in socket rod, design in PCP, and design in ESP. And you have to compare the best design with best design. And then you can make a conclusion, okay? Again, I recommend you to watch the webinar EIPR, because still you are thinking in gas volumes instead of GBF. So you are blind. I recommend you to watch that video, because you missed that part. And the only way to answer that question at the very beginning, check for this one, because gas itself not telling me anything. By the way, I can notice that there is no reservoir pressure there. There is no productivity index. So even with that data, it's impossible to answer. Watch my video of the EIPR. Then that gives you some light regarding the gas, because you have a lot of water. So that will be my first opinion. After you watch that, then you try to do the right socket rod design, the right PCP design, the right ESP design, and then you can get a conclusion. Check for the capital expenses, operational expenses, and so on.
Okay. So thank you very much.
The casing is not there. There are many things that with that information it's not possible to give you.
Okay, Laura. And also you can contact us our email.
You can request for a mentoring or consulting for that case.
Yes, and also we want to invite you to our next training, online training, with Mr. Caicedo.
Which is in ESP, right?
Yes, it is.
The course is going to be online in English, but if there are no only people who speak Spanish, then I'm going to give the course in Spanish. But initially, it's thought to be for people in US. But if all of them that speak Spanish, they feel comfortable in Spanish, I will teach and provide the material in Spanish.
Okay, excellent. So thank you.
And this afternoon also, We have a on life of limiting factor for soccer road applications. What is a interactive online session? Okay.
Yes, you can watch. You can see us in the Instagram in like UPC Global or our YouTube channel also. So thank you very much for your time, for being here today. Thank you, Sergio, for your explanations and for your time also. And have a good day. I'll see you soon, everyone.
Thank you for your time, guys.
Bye.
Have a nice day.